We'll get going. So welcome to Cambridge Carbon Footprint and Open Eco Homes. My name is Antony. It's my great pleasure to chair the session today. So if you're thinking about making your house more energy efficient and in particular more airtight, you really need to consider ventilation. But what are the options? I experienced this when we renovated our 1930s house a few years ago. We installed a mechanical ventilation heat recovery system, or an MVHR. And this was great, but it was costly. Putting it in was very disruptive. And it really makes sense if you're going for a high level of air tightness. So I'm delighted to find out more about what the options are today. But before we go further, could I introduce Nicola, who's another Open Eco Homes host?
Hello, everybody. Yes, I'm Nicola. I organised this talk. Last year, one of the Open Eco Homes tours was of James's home. You may have seen it. It was the getting off gas one. So we were all terribly excited by the heat pump thing. But he also had this interesting issue about ventilation. He said they previously had quite a lot of problems with damp and mould, and he was a bit worried. So when they did all their retrofit stuff, they also did some ventilation, and he looked around and he chose Airico, a demand control system from Airico, which was cheaper to install than MVHR would have been. Both Antony and myself actually got MVHR in our homes, but the Airico system is easier and it takes up less space, and he said it was actually great. He can't be here today, but he says he's very happy. He just forgets about it, and the damp issues have gone away. And it's not too noisy. It's quite quiet. They're not at all bothered by the noise. So it sounds really great. James had this Open Eco tour, which is a video thing, and Vince had a part in that. People were very interested in it. So we have invited him back. He's very knowledgeable, very experienced, and a great communicator. And so he's going to have his own show today. Thank you.
So just before I introduce Vince, I'd like to do a little bit of housekeeping. Welcome again to this Cambridge Carbon Footprint Open Eco Homes event. Please make sure you're familiar with the controls at the bottom of your Zoom window and mute yourself. If you want to speak later, for example, in the Q&A, you'll need to unmute, and it needs to be you doing that. If you have any requests for clarifications or questions or comments or suggestions, please write them in the Zoom chat, the speech bubble at the bottom. Nicola will be monitoring that during the call. I'd just like to say as well that this meeting is being recorded. You've probably been given a prompt to highlight that. We really welcome seeing you, but if you'd rather not appear, please make sure that your Zoom video camera is off. Slides, the video recording and chat are going to be emailed to bookers in a day or two. So let's introduce this presentation where Vince will give a really expert view of the trade-offs that Nicola was talking about. Vince has been in the heating and ventilation industry for over 20 years. He's focused predominantly in the social housing sector, and in particular helping social landlords overcome issues with condensation, with damp and with mold, the sorts of challenges that come from an airtight home. But he's always been interested more broadly in energy efficiency and renewables. And whilst Vince's work at Airico is predominantly in social housing, decarbonisation projects and retrofit are becoming more important, and that's going to just grow and grow over time as we need to retrofit the vast bulk of the UK housing stock. So without saying any more, Vince, let's hand over to you. Really looking forward to your presentation.
Antony, thank you very much. Nicola, thank you both for a very warm welcome. I'm very, very happy to be here and having a chat this evening. Just to sort of pre-warn you, when I sent over these slides, to Antony, quite rightly commented that there's probably a lot more here than we're going to squeeze into this session. So what I'd say, you will get a copy of this in PDF. There's some slides a little bit more at the end, which have I frozen?
No.
No, okay, that's great. Sorry, I could just see the video, my video that I've frozen. So yeah, so there's some slides at the end where there's quite a lot of just writing in there, and I think certain aspects I'll just flick over these, and then you can use these slides as a reference to look back at them a little bit later on. So I'll just kick off, and hopefully this will go on to the next one. So these are the items that I'd like ideally to cover off today. Why we need ventilation, MEV and MVHR in retrofit, and those anagrams mean mechanical extract ventilation and also mechanical ventilation with heat recovery in retrofit. Talk a little bit about the strategy of demand control ventilation. Also, I want to touch on PAS 2035, which is the publicly available specification. It's all about retrofit, and the 2035 is basically the target, for that year, what we're looking to achieve in terms of carbon reduction and what we need to do to our properties in order to achieve that. And also just going to touch a little bit on Aeroco quality standard, which is something that we've introduced into the marketplace, and hopefully some others will follow. So the burning question, why do we need ventilation? Well, certainly properties are becoming more energy efficient. I mean, it's the right thing to do. We want to reduce carbon. That's either through legislation, building regs, through retrofit measures that we want to do ourselves, or some of those that are being funded. And ultimately, we want to achieve higher levels of insulation, air tightness, and to reduce, or if possible, eliminate infiltration. I'll get onto what that really means in a second. So we're certainly spending a lot more time in our homes, up to and sometimes beyond 90% is an average. And within those properties, a typical family of 4 will produce 16 litres of moisture in a week, which is quite a lot to deal with. Can be more. The air inside our homes can actually be up to 5 times more polluting than the air outside. And we know overall air pollution has been linked to an estimated 40,000 premature deaths in the UK alone, and certainly has been labelled a public health emergency by the World Health Organization. It's also known to be a major risk factor for childhood asthma as well. And I think that I really like this slide because it kind of demonstrates how what we can consider indoor air quality, what is good indoor air quality. And certainly the experts that I'm speaking to will say, okay, you can measure things like CO2 or volatile organic compounds, but the reality is that moisture is still the best measure in terms of understanding indoor air quality. So this chart shows an optimum zone for inside of our homes, which you can see there is between 40 and 60%. So the content of the air that contains moisture is between 40 and 60%. There's then a list of things like bacteria, viruses, fungi that will sort of be on either side of that, but not so much in the middle. So that's why it's considered to be the optimum zone. And if you can get somewhere around 50% at all times, you've got a very good environment there. The one that I want to pick out in particular is mites, dust mites. And we can see, I don't know if I've got a pointer here, that really starts becoming quite prevalent at 55% humidity and upwards. And the World Health Organization have linked mites, or actually the feces of mites, to asthma. And what we find is that they tend to reproduce a lot more up at 55% and onwards. So by keeping that at bay, it can actually have quite a big impact on asthma sufferers, for sure. So what we also find you don't really want too much moisture in the building. You don't really want too little either. Certainly when you're getting above this area, sort of 65% relative humidity onwards, what you're going to find is an excess of moisture in the property, and that will lead to condensation. And ultimately that's the perfect environment for mold spores to grow and start their germination process and just carry on. So there is a link here, which is really good. It's from the UK Centre of Moisture in Buildings. It just talks a little bit about getting the right balance within your property and why there might be condensation and mold issues within. So there's some of the terminology that we use. Infiltration is certainly the uncontrolled entry or exit of outdoor or indoor air from the habitable space. Ventilation itself is the controlled or designed replacement of stale indoor air with fresh outdoor air. And air tightness is the thing that we're wanting to get better at in our buildings. It's the elimination of uncontrolled air infiltration. So basically just getting rid of all those drafts. And we've seen here just building regs alone over the years. This is showing the air tightness levels and what we're seeing. Pre-1995, you were getting air tightness of around 13 or just below. 2002, that was dropping under 10. 2006, we were seeing it just below 7. And 2016, we're just below 5. I mean, other parts of Europe are much less than that. In Republic of Ireland, it's actually at 3. So we tend to see that that's coming over here. And I'm not 100% sure what the new regs are going to be with the future home standard, but I think it's more likely to go in this direction than the other direction. So we can imagine that there'll be a lot less, a great improvement there. So we know it's going one way, and certainly when we're retrofitting properties, that's the thing that we're doing. We're making them more airtight, and that in itself is actually putting a greater strain on the ventilation and something that we need to consider. So these are typically the areas that we'll concentrate on and try and eliminate the drafts to make the property more airtight. Doors, 11%, floors, walls, ceilings, 31, windows, always a good one to start with as well. And certainly things like fireplaces can create a massive draft all the time as it goes. So that's just some of the areas that we're concentrating on as we improve our buildings. So as a designer, or even if it's your own project, there is something that we're trying to achieve, or I like to think that we're trying to achieve, which is thermal comfort, which is simply defined as that's condition of mind which expresses satisfaction with the thermal environment. The things that we can have some impact on, certainly as a designer, is the ambient air temperature, which range between 18 and 23 will suit most. Mean radiant surface temperature of the same, between 18 and 23. Relative humidity between 40 and 60%, and airspeed of less than 1 meter a second, which is basically just getting rid of those drafts. Things like clothing level and metabolic rate, that's something you can't control. That's very subjective, and certainly something that a designer won't be able to influence. But the age-old adage is, if you take your building, build it tight, and then ventilate right. So what we've been guided by is Part F. It's the building regulation for ventilation. It's been around for some time now, and not a lot, frankly, has changed in that time. We are seeing a bit of a revamp consultation going through at the moment, but it can be, I suppose, a lot of the time it can be okay. The guidance is good, but it is ultimately a guidance document, and it is based on many assumptions. And I think when it comes to your own property, a little bit more, I suppose a little bit more needs to be looked at in terms of the occupancy, the size of the property, the air tightness of the property, heat losses, all these other factors that Part F doesn't really take into consideration. It's a much more broad brush approach. I mean, in actual fact, you can break it down quite easily in Part F, which it basically says that you shall not suffocate or poison homeowners or turn the property into a mushroom farm. Secondary to that, try not to waste energy in the process. And that is literally that line there: there shall be adequate means of ventilation provided for people in the building. So that can cause a problem if we are just working to Part F, because you can have a compliant property, but it might not actually be performing as it needs to. And that's where we can see some issues with properties where we've gone about, we've done the right thing, we've looked at improving the air, the air tightness, the insulation, and actually what's happened is there's unintended consequences because the regulations just aren't fit for what we're trying to achieve at times. I guess my point on this is it's kind of difficult to expect one product to work everywhere. It will some of the time, equally it won't a lot of the time either. So this actually is a slide that I've taken from Parity Projects. They do a lot of retrofit work, and these pies represent a property in southwest London, and all these are terrace properties. So from the front, they all look identical, but what we can see is the size of the pie represents the amount of energy that's being used by each property, and then we can break that down by heading as well as to where the energy is being used, and it's completely different for all of those properties. And I think that's the point, really. We're all very different. We have different lifestyles, and it's quite important to have products and things that can vary and be efficient and work in a way that is efficient and adapts to our needs, basically. And certainly when we look at something like ventilation, the demand for ventilation will vary room by room, and also it will vary during different times of the day as well. So in terms of the systems that we can look at and arguably choose, I've just picked out two types of system. So there's, and the reason for that is I'm assuming that air tightness levels are below 5, okay? And in that scenario, you're basically looking at continuous mechanical extract ventilation, or continuous mechanical extract ventilation with a heat recovery function. So what does that look like? Well, as Antony said earlier, he's got an MVHR system, which is very good. It will give you excellent indoor air quality. It will ventilate every room, and the way that it does that is if we take this property and split it into 2 different types of rooms, and we always do this. We have the moisture producing rooms, so where we're trying to capture that moisture at source, either in the kitchen or bathroom. And in those rooms, we're extracting out to atmosphere. So we're getting rid of that stale air. And then to basically bring in the fresh air, the stale air, we're bringing that in and we're running it through this heat recovery machine, and we're supplying it into, let's say, the bedroom here and the living room here. So in that process, any energy that's being taken out, we can then preheat the air coming in, and it works really well. But it does come with some drawbacks, particularly in retrofit, because unless you're exposing absolutely everything, it can be rather difficult to run all the ductwork through the property. Also, ideally, this machine should be somewhere within the envelope of the building. There's filters in here, and that's something that does require maintenance and should be changed at least every year, sometimes less, depending on what type of filter it is. They can be a bit tricky in terms of balancing them and setting them up. Typically takes about 4 hours to commission this. And certainly there was a meter study that was carried out not so long ago that tested a whole bunch of these systems. And I think 56% of them weren't actually balanced properly or meeting the designed criteria. So, you know, it doesn't mean to say that they're not all going to work, but it's certainly a big factor in terms of making sure that they are set up properly. And one thing that we've probably found a little bit more is certainly on larger properties with low occupancy, that there needs to be heat available in order to actually recover some of that energy. And I know that sounds a bit odd, but I've had properties where they're quite large and only 2 people living in there, and not all the rooms are getting heated. And they've actually complained that it's becoming cold because they're not fully putting all the energy into the property. So I said earlier, you know, I've picked these types of ventilation system based on the air tightness of below 5, and these are typically the measures that you'll be taking that would get you to that level. So we're looking at sort of full, double or triple glazing, secondary glazing even as well. Things like doors with, you know, external doors with draft seals and letterbox seals, and I won't go all through all these, but things like impermeable overlays and edge sealing of suspended floors and airtight membranes, lots of detailing work around penetrations, sealing of things like overflow pipes, and yeah, it's quite a bit of work. But that's just to give you a bit of context on what, you know, if you're thinking, well, am I going to be below 5 or am I going to be over? These are the things that typically will get you there. So, sorry, that MVHR slide was probably a little bit in odd position, actually, but I'll come back to that. So the considerations for a project is, well, what is the goal that you're looking for, you know, and could be how deep is the retrofit. So if you wanted MVHR and you have got everything exposed, that could be the right choice there. Obviously, budget is a key thing. Where the property is located, where you bring air in from, might have a factor, depending on if it's a busy road or something like that. Is there room for the equipment in itself? That's something that's normally a bit of a battle, trying to find a home for this plant, you know, this equipment. Again, noise pollutants, that could be something to do with, you know, what the location of the property. Got to think of things like ongoing maintenance, timescales. That's quite a key thing now, particularly where we're seeing breaks in the supply chain. Other things on the property, you know, is there a basement present? If you've got a fully tanked basement, you'll absolutely have to supply that air mechanically. So that might, by default, mean that MVHR is the only suitable product for that particular property. How you introduce the fresh air, and Other things like, primary energy usage, the commissioning, there's a lot, I guess, to consider. There's a little quote there from Professor Tim Sharp, who's, I guess, talking a little bit about SAP being used as a tool to specify products rather than actually looking at the products themselves. But anyway, I'll let you read that. So just going on, still looking at the MVHR. Sorry, I think that other slide should have been before this one, but my apologies for that. So typically this is how an MVHR will work. Drawing fresh air out from outside and the stale air coming from the property here. So as one is passing over the other, we can get a higher temperature in and virtually nothing going out in terms of temperature. Good system, not always the right system, depends on the project itself. So Ian Mordett, very, very professional chap, does a lot of an expert for building regulations, Part F. He said if we did wet systems, the way ventilation generally gets installed, there would be water all over the floor. It wouldn't be tolerated, obviously. Yeah, because it's air, people just don't get it. The installers, the commissioners, the users, they don't care or just don't notice. There's someone that's worked in the ventilation industry for some time, but it is key. We do need to make sure that we do actually add a little bit of thought and make sure that these systems are going in correctly, because the consequences otherwise are rather bad, and generally they're visible through things like mold. This is just a quick slide about an imbalance of an MVHR machine, and the importance of setting that up. And whatever you're extracting out from a property, you also need to make sure that you're delivering the same volume of air back in. Otherwise you get this imbalance. And what this one is showing is that there's 30 cubic meter imbalance on the machine, which is costing about 9 pence a day in terms of extra consumption and lost energy. So it can be a key thing. It just comes back to that commissioning on a property. I've put this slide in as well because we tend to just say, look, MVHR, if you've got an airtight property, that's the only time to use it. And this was a project that was done by our MVHR product manager, which was a beautiful looking building here, not airtight in the least. But MVHR was used because one thing that it could actually do is ensure that where you want fresh air coming in, you could actually push that in exactly where you wanted it. So that project was more about having good indoor air quality, but the heat recovery element of it just didn't matter to this particular client. And it was, again, just, what was the goal for this particular property? It was indoor, good indoor air quality. So that, I suppose it's a bit of a myth bust, if you like, but it doesn't always have to be in these airtight properties. So that's sort of broadly speaking about MVHR. So an extract system, or MEV, isn't as efficient, certainly because it's just running all the time. The only way that you can add some efficiency onto that is by having it demand controlled or having it adaptive. And there's lots of talk about this in the code for practice for control of condensation in buildings, for argument's sake. That talks about an ideal ventilation system which is controllable and it responds to occupancy and can extract air from the moisture producing areas and during periods of high moisture generation, and it replaces it with a controllable amount of outdoor air flowing in via the other rooms. So that would regulate the amount of air required to remove moisture at source, prevent its spread, and ventilate the whole building with outdoor air in a controlled manner. So lots of references to control there. Now, there are sort of various methods of control, if you like. There's certain definitions. You can have things like manual override controls and fan speed controls and presence detector, and they're things that will have, to a degree, some control over the ventilation. There's also other things like humidity control sensors, which will ping on and off at certain percentage. So typically a lot of these actually kick in at about 65% humidity, which arguably, the environment has already gone beyond what it should be. What we're looking at, certainly with our systems, is something that's adaptive, and it will basically always be operating to achieve that, that optimum zone, if you like. Whether that means that extracts are opening or closing, depending on the amount of moisture in those rooms, or how much air is coming in is being controlled as well. The whole system works on a room by room basis. And maybe this slide shows it a little bit better. So this graph here actually shows a 24-hour period in a property in France. And what we've got here is the percentage of humidity. So the pink line is actually showing what the extract amount is for one of the fans, which is sitting there about 4 liters a second most of the time. And we can see some spikes in activity. This is the amount of humidity that's being recorded in the property. And as this is France, everybody comes back for lunchtime, and we can see a massive spike in humidity here. But interestingly, the fan actually does the same thing. It's responding, and actually gone from, say, 4 liters a second, it's now delivering 12 liters a second. And what we can then see is, as the humidity is reducing because we're ventilating more, also the extract rate is reducing as well. So we're more or less mirroring, the fan is working harder to get rid of the moisture as it's being produced, and it's reducing its extract rate as necessary, as the humidity isn't so great. Just so you know, France is typically a less humid environment, so that if we did that in the UK, we'd see a different graph, which I have got on other slides. So yeah, these are sort of the key factors, if you like. We know every room or building has a rising and falling demand for ventilation. It could be moisture, carbon dioxide, or something else. The real challenge, certainly for any fixed rates, is picking a rate that covers all the bases, something that sits in quite nicely amongst all of those. The problem with that, if you pick a rate that's too high, you're going to over-ventilate a property. That's going to lead to comfort issues, unnecessarily taking heat out of the property. If you fix a rate too low, you're more than likely going to be under-ventilating the property. So that will lead to an excess of moisture. That in turn will lead to the issues of condensation and mold. So it's just one of those guessing games you can't get right. So if you can somehow follow the indoor air quality and have something that can adapt itself when appropriate and ventilate greater when it needs to or less, then you end up with two things. One, that you're managing the moisture in the property. Two, you're saving energy as well. And there we go. That's just a visual representation of that. So the typical components of the system, there'll be a fan to extract. That would be somewhere in a property. We can have multiple fans if necessary. That's what we did at in James's property, because we had a fan on the 3rd story in the attic room, and we also had another fan in the kitchen for the kitchen and WC. So, you know, you can be quite flexible in terms of where you place these and how many as well. We have this demand controlled exhaust unit, which will adapt itself in the wet rooms or toilet, kitchen. So these are the ones that are pulling out the air. And then we have some control over where the air is coming in from, whether that's a trickle vent like this. We also do a wall vent, which is not shown here. And the idea is that if there's moisture buildup in this, in the double bedroom here, this will allow more air to pass and to come into that room. And the cross airflow through the doors, the moisture will then be taken out by the nearest extract point. How am I doing for time? Oh, okay, I really, yeah. I think I've got a lot to get through already. But anyway, so typically it looks like this. You're extracting out of the wet rooms to a larger fan, and that's going out to atmosphere. So the good thing about something like this is it can be quite quiet. Key thing is that the wet rooms you're extracting from those, and the makeup air you're bringing in either through the living room or through the bedrooms, the habitable rooms, and you don't have any noise. There's nothing powered here. So it's just literally regulating itself to open and close as necessary. I'm going to just come on to this slide actually, because one of the things that heat recovery is very good at is actually recovering that energy. This was a study that was done for 274 passive house properties in Belgium, and they thought it'd be quite interesting to compare heat recovery and demand control ventilation. So you can see the C+ properties here have been fitted with a demand control system, and the remaining D1s are MVHR. So there's quite a good sort of split of those. What they found is actually there wasn't really any difference in terms of the indoor air quality. They were both comparable. They looked at a 15-year sort of idea of how much it costs, capital cost and running costs. And what was quite interesting on that, you got a slightly higher capital cost on the MVHR. The electrical consumption to run the unit was actually 4 times as much. And the heating consumption, there wasn't actually that much difference between the properties. Yes, the MEV, you did have to put more heat into those properties, but there wasn't as big a difference as you might think. And then the maintenance and the ongoing maintenance, obviously with the filter replacements and things, meant that was a bit more for the MVHR. So they calculated over 15 years, it would be about 18,000 euros for the MVHR and just over 12 for MEV, which is, I thought, quite an interesting study, actually, that one. I have got that in more detail if anyone wants to have a look at it. I am conscious of time here. Shall I continue on? I'm sort of asking you, Antony and Nicola.
I think perhaps if you can wrap up in the next sort of 3-4 minutes, that would be great.
Yeah, that's fine. That's fine. So I did touch on PAS 2035 earlier, and certainly talking to the author of that, Dr. Peter Rickaby, he's had many years' experience doing retrofit in the industry. And he ultimately says that the whole point of that document is it's almost a Bible of learning from all the things that we've done wrong in the last, all the retrofitting disasters, and learning from that. And he said, more than anything, the biggest risk when doing a retrofit is moisture. It's managing the moisture risk. So that was the sort of the key thing, and I guess why I'm a bit of an advocate of what we do. And certainly when you're taking a property and modifying it, one of the key things that you really have to look at is obviously the ventilation. This is just an assessment from that, in terms of, well, what have you currently got? Is there any evidence of condensation or mold in the property right now? Is the system working? Is it working but incomplete? And a lot of people don't realise that they might have an incomplete ventilation system. Is there good intermittent extract or passive stack? But ultimately the design of the property is going to be below 5. And if there's any of those factors, then you've got to look at upgrading, if you like. And the key thing there is making sure that when a design is done, the system has got capacity built into it, certainly based on full occupancy, and it can be beyond that as well, so that even if you're looking at doing measures further down the line that could improve the air tightness, you're not going to run into any issues with excess moisture. And demand control being a key thing to ensure energy efficiency. So I think for now, I'll come out of that because, we're more or less there, actually. Yeah, we're more or less there. I think the only thing that I was just going to add on to that from our perspective is just a little while back, we put something together called the Erico Quality Standards, which was, I suppose that a lot of the failings that we've seen in the industry is just where a lack of knowledge or nobody really checks to see what's going on. So we just wanted to have a much bigger part of the process, in terms of designing systems, overseeing the install if that particular person wasn't familiar with our product, and importantly testing and making sure that what had been installed met the design criteria, and if it didn't, that it can be rectified to make sure that it does. So we put this forward, and it would be great if some other people followed the same path, but it's a free service. It's all part of it, and that's the flow chart, if you like, on how that works. So I think that's quite a nice place to draw that to a close, actually, and say thank you for your attention.
Thanks, Vince. We do have quite a few questions, so
oh, good.
Yeah. As you would expect, I think.
Yeah. Let me stop sharing this, and then we can get back. I know that it's quite a lot of information there, and probably, it's always difficult to know where to pitch it, to be honest.
I think that was a great summary, and as we highlighted, we'll be sending around the video and the slides afterwards, so people can go into more detail at their leisure. Nicola. Yeah.
Andrew, do you want to unmute and ask your second question, which was the one about the London high humidity?
Yes. Hi. Thanks for this talk, by the way. Yes. I mean, it's just a weird one, isn't it? Because I'm learning all about this kind of stuff. And when I found out that actually the humidity outside, on average, I mean, right now it's 75% humidity, and we've got 70 to 80% a lot of the time. And London, as you probably know, is on average is 70% humidity. So I got that weird thing when I was learning about it, and like, we've got to reduce the humidity internally of a house. And then also all the stuff about having an open moisture walls, so that moisture can go through and all that kind of thing. Water vapor can come in and out the house, and that's all cool because we've got our old bricks. And then it turns out actually that if we get our house down to 50%, which is this good level, then the vapors are going to be forced through the walls.
Well, let's first things first, I suppose. When we're measuring humidity, It's probably more important to be aware of that during the winter months, because that's typically when we're going to see bigger issues with, doors and windows are typically kept shut. And also when we're measuring indoor air quality, we can't, if it's high humidity outside, that's not an issue when it's a day like today, because we don't have any control over what the atmosphere is outside. What we're actually looking for is we want to take away any potential moisture rise. So the activities that we're carrying out in our own house, whether that's washing or cleaning or metabolizing, we want to make sure that the ventilation that's present is actually dealing with that on top of what is already there. So when we do, we do quite a lot of, it's called vapor pressure differential, and it's understanding, well, what is the content of the moisture in the air? What's the temperature outside? Above that, what are we actually, are we dealing with that in terms of ventilation? Because the best ventilation on the planet is just open up all the windows. That you can't get better than just opening up all the windows and doors in the house. I've been doing it all today. That doesn't become practical during the winter months, typically when it's colder outside, and then you have to differentiate and understand what the air is doing and what the moisture is doing in that air at different temperatures, because we know the holding capacity of air rises as we heat it up. So if you had a sort of, cubic meter of air, its holding capacity would be much greater at a higher temperature, whereas it's more likely to hit its holding, its dew point at a lower temperature. So I wouldn't get hung up on that, in terms of indoor air quality. If we're maintaining what it is outside, that's okay. If it's a bit hotter inside than it is outside, that's probably when you'll start to see a bit of a reduction in humidity if you're measuring it. But it's more critical in the winter, for sure.
Thanks. Nicola, do we have another question?
Yeah, we got lots of questions, but I just want to clarify one thing, sorry. But if you've got 70% humidity in the summer, does that mean that Air Eco is going to be running all the time to reduce the humidity when it can't, because it's the same outside as it is in?
Yeah, basically. I've got, I can send you a link actually. We've done quite a long-term study of this using Hall effect sensors and things. And I think we're 12 years into this test now. So we got quite a lot of data on that. But it's probably explained in a lot more depth and by somebody more intelligent than me on this, which is about half an hour long. Yeah. So
I look forward to that one.
Yeah, but you're right. I mean, it will. It's all relative, though, isn't it? It's all relative. But yeah, the sensors have a range between 35% and 75%. So if it's higher humidity, then it will be open more. Yeah, sure.
Okay. Next question. A quick one, I think, from Antony actually, about filters.
So one of the things I really like about the MVHR system that we've installed here actually is specifically the filters. We have much lower hay fever, for example, in our house. And my goodness, you should see the kind of street gunk that comes out. The filters are black when we change them. How does that work with the MEV systems?
Yeah, well, there's no filters in there. And I think it sort of goes back to what the primary concerns are. And you're absolutely right. Filters, MVHR undoubtedly is the gold standard in ventilation. Can't get away from that. It absolutely is. And if that's sort of one of the primary concerns, then definitely go for that system, undoubtedly. I think on a lot of projects, it all depends on what the compromise is. And some clients I've been speaking to is, well, I want a marble worktop in the kitchen. So, so the MVHR is sort of, almost dumped for that reason in favour of a slightly cheaper alternative. I'm not here to knock MVHR. We do, sell it, and it's a great product. It really is. I think in retrofit, it can be really difficult to retrofit. Yeah, but then if your goal is, just like that sort of castle type building that we looked at, if IAQ, indoor air quality, is what it's all about, and pollen reduction and things.
Yeah,
absolutely. Yeah.
Nicola.
Yeah. Okay. Next question from Alana.
Hiya. So I was just curious what your rationale is, or the general rationale is behind using moisture rather than CO2 or other measures of air quality when you're looking at ventilation.
It's a good question. I mean, we do use CO2 as, we manufacture CO2 sensors. What we found when we're actually measuring pollutants is actually, it's much easier to pick up on moisture. It's a much easier thing to measure. And there are some good CO2 sensors out there. We use two lasers, a control one and one that's actually measuring what the CO2 is. One of the sort of issues that you have is you're not actually sure where the CO2 is and what the concentration levels are maybe at the extract point versus, let's say, a bedroom. So you then sort of get into the realms of saying, well, what is it that I want to measure, and how effective is it? What we've found is when we've measured moisture and CO2 together, they pretty much go in parallel. And if you're dealing with moisture, by default you're dealing with all the other contaminants, and it is like I say, just a much easier thing to measure.
So would that be the same in bathrooms and kitchens that are generally more moist, that the CO2 would also go in parallel there?
You typically, I mean, if we put it on a context of let's say an MVHR system with some really good controls behind it, you'd typically use CO2 as in the habitable rooms. So what you would then do is look at how many parts per million you're picking up, and you might start supplying more air into those living rooms or bedrooms to bring that level down. And then on the other side, where you're extracting out of those wet rooms, that would still typically be done by relative humidity. So yeah, it's kind of a different strategy for those different rooms in that scenario. But we found that moisture and CO2, I mean, generally CO2 is there through metabolism. So you tend to find, the water vapor, if you're picking up on that, like I say, by default, you're picking up on the CO2. I mean, there are other things like VOCs, and don't get me wrong, we do use CO2 sensors where, we had a hot yoga studio. So, you're in a scenario where you've actually got high temperature, you want that high humidity, and all of a sudden moisture isn't the best indicator of indoor air quality. It actually becomes CO2 in that scenario. Just for argument's sake, you can measure it that way in different scenarios, but typically we found, the domestic properties that we're in, that's the best way of doing it. I hope that. Yeah. Okay.
We have got much more time. We do have quite a few more questions. John, can you ask your one about your air from the next door?
I can, yeah. Hi folks, thanks.
How you doing?
So we're in a semi-detached house, and we had a problem, we still do really, all those, with air leakage between the houses.
Oh yeah.
And there was the main issue we had initially was about smells and stuff, but obviously it's a question I can't quite get my head around, is if we're trying to control airflow and we haven't slightly unknown exchange with the next door neighbours? Are we going to just be blowing air into their lounge or sucking it out again? And I don't know, what's your view on that?
It's that thing with permeability, isn't it? Again, you know, the infiltration. I suppose we're seeing this with some of the retrofits that we're doing at the moment, more in terms of energy loss, actually, where we've got a semi, and it's, you know, you're doing one side with massive amounts of energy efficiency measures, insulation, air tightness, membranes and such. In that scenario, they're just trying to do more, like on the gable, sorry, not on the gable wall, but on the the party wall, to try and prevent anything sort of coming through that way. But the thing is, you're going to have open, you either have closed vapor properties or open vapor properties. And I guess with smells, that's kind of a bit of a challenge. But if you have, I guess, arguably a greater airflow, you might dilute some of those smells if you've got a bit of airflow going through. Not always the case, but air movement generally can get rid of smells, and that's something that ventilation is tasked with doing in things like toilets. I honestly don't know what the answer is. It's quite specific. But the open vaporness part of it is, you know, that sort of saying, well, look, you know, I'm quite happy to have moisture coming into my building or air, and I'll deal with it when it's there, you know, and then get rid of it. I think some professional help would be a very good idea from someone smarter than me, maybe more of a building physicist. I mean, in my mind, I'm thinking just, you know, almost try and blank it off. But where's the smell coming from? Is it inside? Is it outside?
Yeah, we had it surveyed, and they had a few ideas, but they didn't really find the source. It's definitely an internal transfer.
Yeah,
it just highlighted how complicated it could be to really get it right.
For sure.
And then I guess once you've got an idea of what's going on, it's okay. But yeah, because we can't pin down what the issue is, it makes it quite
tricky. For sure. I mean, look,
if you don't mind, could I ask that we take further questions or further discussion for a little bit later, because I think now is probably a good time to wrap up the discussion. We will be continuing the session if Vince is okay, and I hope there'll be a bit more chance to go into detail on that, and also there have been some other really interesting questions. But Nicola, would you mind sharing the closing slides, and we'll wrap up on the main thing now, so people can drop off if they've had learned what they were looking for. So first of all, really grateful if you could give us some feedback, and I hope, Nicola, if you don't mind dropping a link to the donate form. Now we'll also send the feedback form around in the email afterwards. This event is organised by Cambridge Carbon Footprint, a wonderful charity doing all sorts of great work, and Open Eco Homes is one of their biggest projects, but it costs a significant amount to run, so donations would be greatly appreciated. I'd also just like to direct you to the Cambridge Carbon Footprint website. If you could go back to the previous slide, Nicola.
I had an accident there, it's okay now.
That's okay. Could we go on to the next slide, the one with the other resources? So there's lots more information on how you can get started, and I have to say, as someone who's done this, I really do encourage you to get started. You can make really significant improvements to your house, whether it's through insulation, through air tightness, through draft proofing, and there's plenty of information to help you steer that. Lots of case studies, lots of the talks, and advice available. We'll send more of this round later. But finally, just a big thank you from all of us. Firstly, to Open Eco Homes and Cambridge Carbon Footprint for organising this, but really especially to Vince and Erico for giving us quite an interesting and different perspective and really helping us to highlight, to understand, where is best to use the different technologies available, and that you don't necessarily have to rip your house up to install an MVHR in order to have really good indoor air quality. So we'll wrap up the formal meeting there. You're welcome to stay on, and let's continue.
Can I say one more tiny thing, Anthony?
Great.
CCF have recently acquired some CO2 monitors, which we will be making available for people to borrow, and they're quite handy. They will sort of log every hour what your CO2 is, and you can see what it's doing overnight. So look out for that if you're interested in that sort of thing.
And if you're not signed up, it's easy to sign up on the Cambridge Carbon Footprint website and to get more information on this. The help that's available. They've got a thermal imaging camera and plenty more. So let's wrap up the formal meeting with Vince. Again, thank you very much. Tremendous insight. Hopefully, if you don't mind, we could stay around for a little bit longer for a bit more open discussion.
And if Vince does have to go, then Anthony and I both have some experience with MVHR, so we've got a clue about something.
Yeah, and we can say a little bit more.
Vince, are you able to stay a few more minutes?
Yeah, look, happy to do that. Happy to.
Okay, Tom has an interesting question about multiple fans. Tom?
Oh, yeah.
Tom? He's not there anymore.
No, on mute at the moment, I can see.
Well, I'll ask it then.
Okay, no, I've got there. Sorry about that. So yes, we're doing a retrofit of an Edwardian home, and I was wondering, can we minimise the amount of ducting by having multiple fans in a demand control ventilation system, or indeed, is there a limit on that? Can we do away with ducting?
You can certainly minimise it, Tom. And I did a double barn conversion in where was that? Sudbury, I believe, and that ended up almost like a U-shaped building. And the practicality of getting all of the ducting back to a single point was just so complicated. And I think in that scenario, it was much better to have localized fans to the wet rooms. And I guess probably overall it probably worked out maybe a bit cheaper in terms of the ducting and less time taken to install it and everything. Yes, there was more product and more fans there, but the interesting thing that always concerns everyone is the fact that, well, if I've got 3 fans, they're going to be working harder and using more energy and such. The key thing is the fan only responds to what the grills are doing. So I didn't really talk about the technology, but essentially the humidity sensitive control in each grill or inlet is 8 pieces of nylon. So nylon, essentially, when it becomes wet, it grows in length. When it shrinks, it reduces, and we just amplify that. So the main control is actually done either at the inlets to let the air in or the extracts. So the fan only actually responds to what those grills are doing. So as they open and close based on the amount of humidity, the fan, it won't speed up. And it took me a very long time to get my head around this. It just uses more torque to move the air. So you don't have this step change, you don't have this variance of speed. It stays at the same speed all the time. But and my point is that the fans will only do what's necessary based on what the sensors are picking up on. And it's a really nice part of the system, because most ventilation systems will have a low level and then they'll boost. And actually sometimes that boost can be not particularly pleasant. It could be quite noisy. It can come at the wrong time of day. It could be in the middle of the night. you know, and to have something that's just constant at all times, but has the variance of volume, is quite appealing. Yeah, so, you know, you don't use any more energy, you just have the capacity there. So if you was to have loads of people over, I don't know, let's say Christmas or something, and house is absolutely full, you've got the capacity in the system, it will respond to all those extra bodies. But if it's not been, you know, if that's not the scenario day to day, the system will just run to what it needs to. Yeah.
Thanks.
Yeah. And you can minimize disruption, which is something that you have to be very mindful of, you know, when you're doing these, particularly like Victorian townhouses or Edwardian houses, where typically you get an extension on the property, and the kitchen somewhere at the back, maybe with a toilet or bathroom, and then somewhere else in the property is a bathroom, completely different part of the house. So yeah.
This relates quite nicely to something Andrew asked a long time ago, and we haven't let him ask it yet.
Okay.
It was about controlling the inlet as well as the outlet.
Yeah.
Andrew? Are you still there? Yes, you are.
I'm here. Oh, yeah. It was that thing where, you know, obviously the old days where you had a fan in the kitchen and the bathroom, and it pushed air out noisily, you know, when you had a bath, and then it stopped. And we all, you know, they didn't work. And anyway, so now we've got the new thing is, so we push air out, but we bring air in a controlled way. And I was just wondering, I mean, if we push air out the building, as you well know, you know, that's going to reduce there's going to be a push from the outside to push the air back into little cracks around the house. Or, you know, the air's got to come back in, basically, isn't it? Because to equalize the pressure. I just wondering, why do we need to control that? Why can't we just push some air out in the wet rooms and let it filter back in somewhere around the house in a normal way?
Yeah, I mean, look, I think it depends where you are in terms of the air tightness of the property, Andrew. You know, you're absolutely right. If you have negative pressure, you can put out the stale air, and you'll bring in the fresh air through infiltration or dedicated background ventilators. The issue that you can have with that is air is quite lazy, and it will always take the shortest path of resistance, or the least path of resistance. That can be a problem if you've got, let's say, bedrooms, and you want to control where the air is coming in from, because you might find that you've got a room or two rooms in the house that aren't really being used very much, or have got quite low moisture content or moisture production. And then you might have a bedroom with two people in there that actually needs a lot more. You know, it needs a much greater amount of air coming in. And that's why we like to have the control in the inlets, because those rooms that aren't actually, when there's no need for it, they're virtually sort of in a shut off state. So you're actually managing where the air is coming in, where it's needed. It works much better the more airtight the house is. So when you sort of get into, you know, passive house levels, it works remarkably well. You know, the more airtight, the better, because you've got complete control over where you're bringing the air in from. It's much harder, you know, when it is around that 5 to 10 air tightness of where you're actually bringing the air in from. And we found in retrofit, and this isn't part of the regulations, but we might put in an extract in a hallway. You know, if you've got 3 bedrooms and no bathroom, no wet room, where's your airflow? How are you actually, you know, drawing to get the fresh air coming through? And that's, you know, that's something that you won't find in the building regulations, because it's not a wet room. But if you need to put something in the hallway to manage risk, then you can add that. But it's more about defining air pathways, Andrew, than anything else.
Thanks.
And I think just one more maybe, which is from John. Your question about measuring the airspeed.
Oh yeah, So I'm just wondering about a relatively easy way to try and survey a building or a house or something, I suppose, without having a full airtightness sort of exercise, just to get a simple airspeed monitor and just to sort of see what happens. Is that in any way effective, or is it really impossible to do?
I don't know how effective it would be, if I'm honest, John.
Let's give it a go and see what happens then.
Yeah,
I mean, have a look on that slide that I did earlier in terms of the there's sort of a tipping point below 5, an air tightness of 5, and those measures that I've listed, you know, they came from SR54, which is the Irish retrofit standard actually, and that's typically what they found. If you're doing these things, that's going to give you an air tightness of about 5.
I have to say, John, I looked at a similar thing, and the types of kind of handheld airflow meter don't really work indoors. They're designed to pick up significantly higher flow rates, so you'd need to be holding them right up for a draft. The thing that I've seen that works best is a candle. So just literally, you know, go in search, put all of the extract fans on that you can, so that you've got kind of flow, and go searching, and you'll pretty quickly find things, and maybe some things that you didn't know, and discover that perhaps you're drawing air in. But even that doesn't always work, because the gaps might be the gaps between your house and the neighbours might be in the floor voids, but actually the pathway from the floor void into the room might be somewhere else. So you need a little bit of intelligence. That's one of the tricks they use when they're sealing up kind of passive houses as well.
That's okay. Interesting.
I know I said there was one more, but actually there's another one now. This has to be the last one, Vince, I promise. Absolutely, it's ridiculous. But this is Ruth, and this is a really good question. So please, Ruth. Ruth? Oh,
she's coming.
She's coming. Okay. She's still muted at the moment.
I'll just quickly.
Can you hear me now?
Yeah, that's fine.
Yeah. Okay. Yes. How on earth do you get the air in? I'm just beginning to think about air. Where's the safest place to get it from? From the rooftop? I have asked all my neighbours what's coming out of their chimneys.
So there are some regulations there, Ruth, in terms of where you bring the air in from. Typically, if you're extracting from the wet rooms, so kitchen, bathroom, utility, toilet, then you're extracting out of those ones, but your fresh air will come in through the habitable rooms. So that would be the bedrooms, living room, dining room. The regulations say that background ventilators, which is what they're called, background ventilators where the air comes in, they must be no lower than 1.7 meters from the floor level.
I think we're talking about the outside here, Vince, sorry, not the inside. I mean, do you take it from the front of the house and the back of the house? The roof?
So if we're doing MVHR, for instance, or, I mean, what we do in each room, we'd have if we got wall or window inlets, what we tend to do is put it the furthest point away from the door. So the fresh air that you're bringing in has got the longest pathway to dilute the air. Okay.
I see what you mean. So you're actually bringing it in through the windows anyway.
Yeah. So
yeah. Okay. Right.
So
okay.
I think I've answered the question correctly, but there's two different types, because obviously with MVHR, what you're doing is you're bringing air in through, let's say through a roof. It could be through a wall. But what we try and do is make sure that I like to see at least 2 meters distance between the air that you're extracting versus the air that you're bringing in, because you don't want the stale air that you've just sent out to come straight back in again if they're too close.
Could I just MVHR my roof space on my attic?
So, sorry, Ruth, I didn't catch the beginning of that question. Sorry.
Could I just MVHR my roof space and my 2 attic rooms?
There are yeah, I guess
there are products, aren't there, that are focused on just localized MVHR, so it is possible. Yeah,
yeah, they do single room heat recovery systems. I think my own experience with some of these were the smaller ones in particular, because they have to move quite large volumes at times, they can be quite noisy. So it all depends on how happy you are with that compromise of noise, because that's one of the key things with ventilation, and certainly all the problematic properties that I've been to. When you speak to the person that's living there, say, well, it was too noisy, I switched it off. Can't stop it.
Yeah.
So that's the thing, you know. When does a sound become a noise? I had this explained to me. Well, if my neighbour's daughter is playing a recorder during the day, that can be quite nice potentially. If they do it at 3 o'clock in the morning, that then becomes a noise. It's a nuisance. So, you know, that's yeah. Anyway,
so I think let's wrap up there. But thank you, Vince, for staying on for a few extra minutes. Once again, really enjoyed your presentation. I think we've all learned a lot and have a much better idea about the strengths and the weaknesses. Everyone, and thanks for joining. More detail, you know, there'll be plenty more detail in the pack that Cambridge Carbon Footprint will be sending out after the event. So thanks again. Let's wrap up there.
Thanks for the brilliant questions. I really enjoyed it. All right, good luck in the projects, and maybe I'll speak to you later.
Thank you.